In the latter part of this video, I'd like to talk about aldol reactions. Aldol reactions are the topics of 26A and B. They are actually just another example of equilibrium addition of a nucleophile to a carbonyl, or in the case of Michael reactions, to an alpha-beta unsaturated carbonyl. But they do deserve some special note. So aldol reactions start with an aldehyde or ketone that has at least one alpha hydrogen, like so. And the alpha hydrogen in the presence of a base, and normally these are done in weaker bases, not super weak, but hydroxide or alkoxide, something that would give us an equilibrium with enolate ions. And the base can take off an alpha hydrogen, leave behind a pair of electrons. Here I've drawn it as an enolate ion with the negative charge on the carbon. This now is a reasonably good but not super strong nucleophile, not as strong as our alkylithiums or lithium aluminum hydride or sodium borohydride, and it can add reversibly to carbonyl compounds. Because this is an equilibrium, however, there will always still be some of the original carbonyl compound around. For convenience sake, I'm going to color this second carbonyl compound green. Enolate ions, being nucleophiles, are attracted to the delta positive carbonyl of another carbon atom. And when that carbon atom gets more than 4 bonds, it will break its CO pi bond, leaving the electrons behind on the oxygen. This will give you your new carbon-carbon bond and your first intermediate. Note the new carbon-carbon bond is formed between the original alpha position and what becomes the new beta position of the relative to the carbonyl. So we've got carbonyl alpha, which was the enolate ion, beta, which was formerly the carbonyl, and the new bond is the alpha beta bond. So if we want to designate that bond, we can circle it here. The new bond was formed between the alpha and the beta position. If you look carefully now, this intermediate is very, very close to our final product of an aldol reaction. That is, it only needs a proton to get to the end. This final product is called an aldol, or a beta hydroxycarbonyl. When you see an aldol, a beta hydroxycarbonyl, you can imagine that that was synthesized, or could have been synthesized, by condensation, known as the aldol reaction, or by two molecules combining together to make a new alpha-beta bond. Most aldol products are fairly stable, but if you heat them up or you add acid, you get a second reaction, which leads to a loss of water and a formation of a double bond instead of a single bond between the alpha and beta positions. Let's see how that works in heat and base. Okay, well, if we're still in base, and we still have an alpha hydrogen, we still have another enolate ion we could form. This second enolate ion would normally not be detected because at the end of the reaction you'd neutralize and you'd get back your aldol product. But if you have enough heat or energy available, you will go on to do an elimination reaction that will give you your new product. One of the ways to neutralize the negative charge on the enolate ion is to form a double bond, alpha-beta. The net result of this elimination is to give a new product that is an alpha-beta unsaturated carbonyl compound. In other words, this is a way to make those alpha-beta unsaturated compounds we used in a previous chapter. I want you also to note that the original aldehyde and ketone that made the original enolate ion, here in black, is alpha on over, and the carbonyl that was added to is beta on down. And that in fact we have created an alpha-beta unsaturated double bond between the alpha and beta positions. So if we were to look at a product of an aldol condensation, and the condensation actually means loss of water, and that's what we've lost in these last two steps. So under heated conditions we lose water, we get this condensation, and if you see this product, you know that the alpha-beta bond, where the double bond is the one that was formed in the aldol reaction. Likewise, if you didn't heat, your product would be this aldol, in which the new bond was still made between alpha and beta, but your product would look like a hydroxide position on beta position relative to the carbonyl. Finally, we're going to look at the Michael reaction, which is an example of an aldol reaction. Enolate ion is not adding directly to the carbonyl carbon, it's adding predominantly to the beta position of an alpha-beta unsaturated carbonyl. So the mechanism of this reaction starts off just like the mechanism of aldol reaction or any reaction involving an enolate ion. That is, an added base takes off an alpha hydrogen. We choose a base that will give an equilibrium mixture of the enolate ion and the original aldehyde. Your resulting enolate ion is a good nucleophile towards the beta position of an alpha-beta unsaturated carbonyl. And for conjugate addition, we end up with another enolate ion as our product. Again, the new bond is alpha-beta to the original carbonyl. That is, the atoms in black here on the bottom are the original carbonyl. The blue bond is the new bond between alpha and beta to that carbonyl. And these red ones were the part that used to be the alpha-beta unsaturated carbonyl. After protonation and ketoenol tautomerization, a new carbonyl at the position that had the enolate ion, and your product is now a 1, 2, 3, 4, 5 dicarbonyl compound. So when you see a 1, 2, 3, 4, 5 dicarbonyl compound, it's called a Michael addition product. And you can imagine it could have been made by making an alpha-beta bond between an enolate ion, the 2, 3 position, or alpha-beta to one of the carbonyls.